what I mentioned, the gamma yx, where the indices will tell you which are the two axes that you're talking about. If it's a world line, then you'll have t rt, like this gamma rt. And of course, in the full theory, you'll have more indices. The inertia law related in terms of curvature world line is gamma is equal to 0. The law of gravity inertia particles have world lines which are the straightest possible. In the alleged absence of gravity, we call these inertial particles and say the world lines are straight lines in space plus time. But this is not precise. Where we can in fact discern the presence of gravitational fields, they're everywhere, we see that the straightest lines of space plus time are in fact given by this world line curvature. This is because the presence of matter, the connection on space plus time is not inertia, the connection being the definition of straightness. Free fall world lines are the straightest possible lines in space plus time, so they're the definition of straightness. It's called the connection. The equation of a straightest line includes the connection, which in this case of in the case of inertia is 0 and so isn't seen, but in the presence of matter, the connection curvature is not 0, is given by this. And the straightest lines have this term in them, where what I did here in this equation is instead of writing acceleration is equal to gm over r squared, I took the gm over r squared and put it on this side. Why did I do that? Because gm over r squared is a spurious force. I don't want it on this side of the equation, that the acceleration is equal to some force over m. It's not really a force. It really belongs on this side of the equation, just like inertial forces can be gotten rid of. So I don't want to consider it a force. It's just part of the geometry. And I'll go into that more another time. So we have progressively sophisticated perspectives. Inertia, world line curvature field in space plus time. Then it defined straightness in space plus time. Gravity was also world line curvature field in space plus time. It was the definition of straightness in space plus time. Then we found inertia and gravity are the same thing. They're united into inertia gravity. We got rid of inertia, then we got rid of gravity. People who don't know that these are the straightest possible lines, in other free fall world lines, think of them as curved and invent a gravitational acceleration to explain why they aren't straight. Famous physicist Eddington, one of the physicist mathematicians who first understood and wrote about relativity after Einstein, he said something, I'm paraphrasing, the gravitational force represents the discrepancy between the natural geometry of a space plus time and the abstract geometry arbitrarily ascribed to it. When we naively impose our idea of what it ought to be, we get this, and we get curved world lines. And that's why we think there's such a thing as gravitational acceleration. So when we arbitrarily ascribe a geometry to space plus time that we say, well, it's got to be like this, we end up with gravitational forces. So those gravitational forces are the discrepancy between the natural geometry, which is warped curved, and the one that we kind of imposed on it. Okay, here's just a diagram of when you fly from New York to London, you go over Newfoundland and Labrador and so on. Why? It looks like a very curved line. But if you look on the globe, you'll see that this white line that presents the trajectory of the plane actually is a straight line on the globe. And the one that was straight turns out curved. Because when you look at a curved surface, right, the geodesics are the great circles. And if you just flatten it out onto a piece of paper, you're getting a wrong map. You have to take the surface of the globe, you have to cut it up into, kind of let the edges, right, like you peeled an orange. When you peel an orange and want to make it flat, you're going to have to make it like a flower petal to make it flat. But a map isn't a flower petal. And then you would have like countries separated by this empty space and so on. What they do is they kind of join it in a certain way, so that makes it fake. So you don't get a real true perspective of what the world is like and what the relationships are like and what the geometry is like by looking at a flat map. Only by looking at the true surface. And that's what happens when we look at gravity from the perspective of a non-inertial frame, in other words, like standing right here feeling these inertial forces. We think things are curved, but that's because we're looking at the false map. We should be in a free fall frame, at which time we'll be able to see what straight really means. So basically, Einstein's law of gravity inertia, mass energy gives rise to space-time curvature. And free particle world lines are geodesics of this curved space-time. There's no such thing as a gravitational force. What we're used to calling gravitational acceleration and following particles in orbits, etc., is simply inertial motion in curved space-time. In the presence of matter, there's no departure from inertial motion. Particles are not attracted to the matter, they don't fall into the matter, just that in the space-time region near the matter, space-time is curved. So the inertial world line in the region of space-time, since it is a geodesic of the curved space-time, seems curved in the flat space-time perspective. Okay? So I know that was a lot of material. I covered what I previously did in a few lectures, I did in one, just so that you have this whole coherent idea of exactly now when somebody says to you, Einstein's theory is a theory of curved space-time, and it's also a theory of gravity, you understand why. Okay?